try to describe a scientific career as a branching tree. And our roots are in this work that I've described on the visual system. But along the way, as we've followed our science where it led us, there have been some branch points. And every time you arrive at a branch point, you have to have a very serious think about whether it's worth the risk, this professional risk of pursuing one of these branches. And we confronted that some years ago, about the turn of the century, where we had made a discovery that seemed to be relevant to a genetic disorder called Fragile X syndrome. And our interest in Fragile X syndrome originally was not an interest in the disease. It was an interest in the protein whose absence causes the disease. So this is a protein that is called FMRP. And we're again, basic science, looking at how synapses modify. We came to suspect that there was an important role for this protein, FMRP. And sort of a backstory is that I gave a talk about our work at a meeting, and I sat down, and the guy sitting next to me, who I had never met before, was named Steve Warren, who was the geneticist who discovered the mutation responsible for Fragile X and had an FMRP knockout mouse. And Steve said, "Would you like to look at our mouse?" And I actually called back to the lab, spoke to my then postdoc, Kim Huber, and I said, "Kim, can we look at this mouse?" And she said, "Yes, we can look at this mouse." And so that's how it happened. So he shipped us this mouse that was the mouse model of this disease, Fragile X syndrome. Fragile X syndrome, it's a devastating disorder. It's the most common heritable form of intellectual disability and autism. But in a way, it's a simple disorder, quote unquote simple, because it's caused by the deletion of a single gene. So it's not like so many others that are, have very complicated etiology. This is a pretty straightforward. And so the animal model's particularly valid. So we got the Fragile X mouse, we started doing our experiments, we had a very clear prediction of what we would find. And when we broke the code, we were doing our experiments blind, the results came out exactly the opposite of what we had predicted. And so I stormed into the lab and said, "Somebody screwed up here, you've mistaken the code, and you've reversed the code on these mice." So I insisted that the experiment be repeated, which it was, and the results came out exactly the same, and we were like, okay, we have to rethink this. And it turned out that it became a lot more interesting than what we thought originally. So the phenomenon that we were studying, we had discovered earlier on, requires new protein synthesis at sites of synaptic communication. So it had been known for a long time that the machinery for protein synthesis exists at synapses. It was a lot less clear what the functional contribution of that protein synthesis is. And we had discovered that it was very important for this particular form of synaptic plasticity that we've been studying. And the reason we became interested in the FMRP protein is that it was a protein that was known to be synthesized in response to activating this neurotransmitter receptor that we were stimulating. So it wasn't it was a pretty obvious hypothesis, but as it happened, that it turns out that this FMRP protein is not really an effector of our response, but it's a negative regulator of our response. So the FMRP protein actually binds messenger RNA and puts the brakes on protein synthesis. And presumably the reason it's normally synthesized is because it's a feedback regulation to prevent unchecked protein synthesis.